All right, let's go. Number 6. Matter and antimatter nearly annihilated each other completely. In the first second after the Big Bang, the universe produced matter and antimatter in quantities that should have been exactly equal. This is what the physics demands. For every particle born, an antiparticle twin was created. And when matter meets antimatter, they annihilate, converting entirely to pure energy. If the ratio had been perfectly 1-to-1, the universe would have lasted approximately 1 second before destroying itself in a mutual annihilation event that left behind nothing but a diffuse ocean of photons expanding forever through empty space. No atoms, no molecules, no chemistry, no you. What actually happened, what saved everything, is that for every 1 billion antiparticles that were produced in the early universe, approximately 1,000,000,001 particles of ordinary matter were also produced. 1 extra particle per billion. That microscopic imbalance, called baryon asymmetry, is the reason the entire observable universe exists. After the Great Annihilation, after every antiparticle had found its matter twin and both were erased, that tiny surplus of 1 in a billion matter particles remained. Everything you see, every star, galaxy, nebula, organism, and thought is composed entirely of the leftover rounding error from that event. Physicists have no satisfying explanation for why the asymmetry existed. The Standard Model predicts a preference for matter over antimatter under certain conditions, but the predicted asymmetry is far too small to account for what we observe. Something we don't understand produced the correct imbalance to give the universe a future. We are living inside the residue of an almost total self-destruction. Number 5. The first stars almost never turned on. The early universe was dark. Not dark the way a room is dark the way physics is dark. A uniform fog of hydrogen and helium with no internal structure, no density fluctuations large enough to collapse, no seeds from which stars could grow. For approximately 100 to 200 million years after the Big Bang, there were no stars anywhere in the universe. This period is called the Cosmic Dark Ages. The question of how it ended is more precarious than cosmologists once believed. Stars form when regions of gas become dense enough for gravity to overwhelm thermal pressure and trigger collapse. But in the early universe, everything was almost perfectly smooth. If the quantum fluctuations in the density of the very early universe had been even slightly smaller in amplitude, the density perturbations seated in the first fractions of a second would have been too weak. Gravity would have been unable to overcome the thermal pressure of the expanding gas. The Dark Ages would never have ended. The universe would have kept expanding, growing colder and more diffuse until it reached a state of maximum entropy without ever producing a single nuclear reaction beyond the Big Bang itself. The amplitude of primordial fluctuations is set by physics we are still mapping. It came out at exactly the right value to allow structure to form. Had it been slightly lower, the universe would have expanded in permanent featureless silence. No stellar ignition, no heavy elements, no planets, no evolutionary pressure on matter toward complexity. The cosmos would have died in the dark, never once having lit itself up.
Number 4. The cosmological constant almost won. We exist inside a window so narrow it is almost not a window. When physicists calculate the value of the cosmological constant, the energy density of empty space that drives the expansion of the universe, they find that quantum field theory predicts a value roughly 10 to the power of 120 times larger than what we actually measure. That is not a small discrepancy. It is the largest gap between a theoretical prediction and an observed measurement in the entire history of science. Had the cosmological constant been even a fraction of what the equations suggest it should be, the universe would have expanded so violently in its first moments that no matter could have clumped together at all. No galaxies, no stars, no planets, just a thin soup of particles rushing apart at incomprehensible speed, growing colder and more isolated across infinite expanding emptiness. The fact that the cosmological constant is almost, but not exactly, zero is the single most inexplicable fine-tuning problem in all of physics. There is no mechanism that explains why it is so small. There is no symmetry, no cancellation, no known law that produces this value. Some physicists invoke the anthropic principle. If the constant were any larger, there would be no physicists to calculate it. That is not an explanation. That is an admission of failure dressed in logic. The universe came this close, by a factor of 10 to the 120th power, to being a place where structure is permanently forbidden. We are here because of a number we cannot explain, maintaining a value we cannot calculate, for reasons we do not understand. Number 3. Carbon almost had no resonance state. In 1952, Fred Hoyle made one of the most audacious predictions in scientific history. He examined the universe, noted that carbon, the backbone of all known life, was abundant, and reasoned backward to an uncomfortable conclusion. For carbon to be produced inside stars at the rate observed, an excited nuclear state of carbon-12 must exist at a very specific energy level. Not approximately, exactly. If that state did not exist at precisely that energy, the chain of nuclear reactions responsible for building carbon inside stellar cores would proceed far too slowly, and the universe would be almost entirely devoid of the element. Hoyle announced this prediction before the nuclear state had been measured. He was right. The Hoyle state of carbon-12 exists at 7.6549 MeV, almost perfectly aligned with the combined energy of a helium-4 nucleus and a beryllium-8 nucleus merging inside a stellar interior. This coincidence between the energy of reactants and the energy of the resonance state in the product is so precise that shifting it by even a few percent would collapse carbon production to negligible levels across the entire universe. Life as we know it is built on a nuclear coincidence. The strong nuclear force, the electromagnetic force, and the weak nuclear force are all calibrated by whatever mechanism set them to produce exactly the resonance that makes carbon abundant. No one can explain why. The Hoyle state sits where it must sit for us to exist, and it sits there for reasons that remain, after 70 years of investigation, completely unknown.
Number 2. The Moon almost wasn't large enough. Approximately 4.5 billion years ago, a Mars-sized protoplanet called Theia collided with the early Earth in a grazing impact that ejected an enormous plume of molten material into orbit. That material coalesced into the Moon. Had Theia been smaller, or the impact angle more direct, the Moon would have been a fraction of its current mass. This matters more than most people realize. Earth's rotational axis is tilted at approximately 23.5 degrees, and that tilt is what drives the seasons, distributes solar energy across latitudes, and prevents the poles from becoming permanently, catastrophically cold. Without the Moon's gravitational stabilization, that axial tilt would not be fixed. Simulations show that without a large Moon, Earth's axial tilt would oscillate chaotically between 0 and 85 degrees over timescales of millions of years. At 85 degrees, the poles would bake under continuous sunlight, while the equator froze in permanent shadow. Every climate system would collapse. The hydrological cycle would become unrecognizable. Stable long-term environments in which multicellular life can persist and evolve over hundreds of millions of years would be essentially impossible to maintain. Mars has no large Moon. Its axial tilt has varied from nearly 0 to over 60 degrees over geological time.
What we find on Mars, a frozen, desiccated, geologically dead world, may be what Earth would look like without the product of one specific oblique impact 4.5 billion years ago. A slightly different angle, a slightly smaller impactor, and the platform for complex life on this planet never stabilizes. The evolutionary clock never starts. Number 1. Inflation lasted almost exactly long enough. In the first 10 to the power of -36 seconds after the Big Bang, the universe underwent a period of exponential expansion called inflation, in which space-time itself expanded faster than light, stretching quantum fluctuations into the density variations that would eventually become all large-scale cosmic structure. Inflation ended when a field called the inflaton decayed into the hot plasma of the early universe, and here is where the terror lives. The conditions that allow inflation to end, and to end at the right moment, to produce a universe that is flat enough, smooth enough, and structured enough to allow galaxies and stars to form, appear to require an extraordinary degree of precision in the shape of the inflaton's potential energy landscape. Had inflation ended too soon, the universe would be too lumpy, dominated by catastrophic density fluctuations. Gravitational collapse would have produced a cosmos of black holes, with little or no ordinary matter remaining in stable structures. Had inflation continued even slightly longer, the quantum fluctuations would have been stretched to scales too large for galaxies to form at all. The universe would have been perfectly smooth and perfectly dead. The inflaton's behavior sits in a corridor of parameter space so narrow that it raises the most uncomfortable question in all of cosmology. Why was inflation calibrated to produce this particular universe and not one of the vastly larger number of universes that inflation could have produced instead? We have no answer. We have the universe it produced, and we have a growing, documented list of reasons why almost any variation on its initial conditions would have made that universe uninhabitable, permanently, without exception.